Okay. So, second part. Flow of a vector field. Now, I'm not completely sure because I haven't planned in detail every hour of the course yet, but we will be needing more vector fields than differential forms. That's why I skipped a bit on the differential forms. Now, a very important concept related to a vector field is that of the flow of a vector field. This is, I mean, if you are having trouble with abstract manifold, you can think about submanifolds of RK. Okay, this should be another character, but this should be the Gothic X. But anyway, take a vector field on a manifold. Given an interval, a curve, so from an interval to M, a curve will always be a map from an interval, a real interval, to the manifold. A curve is called integral curve for X if the tangent vector, if X at a point of the curve is equal to the speed of the curve at that point. So to the tangent vector of the curve at that point. So if this holds on the whole of the interval, you say that the curve is an integral curve for the vector field. In some sense, it moves following the vector field. If you think about the vector field being a field of velocities for a fluid or whatever you want, the integral curve is the trajectory of mass point subject to that velocity field. Now, given an open set in M and an interval in R, a map from I times V to M is called the local flow of X if, okay, a notational thing. I is the time, okay, is understood as a time variable. So if at time 0, every point goes to itself, and if you fix the point and you follow the point through time, obviously you get a curve because you are fixing the point V, so you are varying only the variable t in the interval. So if you do that, you obtain an integral curve for X for all P. So an integral curve is what? Is taking a vector field, a field of velocities, for example, for some fluid, having a mass, a point mass, and following the point which is pushed around by your vector field. This gives you a curve inside your manifold somehow, and this is an integral curve. Now you follow all the points at the same time. So you take all the points of some open set in your manifold and follow them under the action of this velocity field or whatever you want. Now what happens? What does it mean that you follow them? That at each time you look at where did the point P go. So you take a point P, you let some time pass, and you look at where it landed. Now you take this ending point, and this is the image of big phi T P. So is where the point P goes after a time T under the action of the field X. I hope this is clear. It's a very intuitive concept once you grasp it, but writing it down is a bit painful, as you can see. It's called the local flow because it's defined only on a set V of M. What could the problem be? Okay, let's stay in Rn. And well, no, we will be addressing it later, I hope. Now, here, flows and ordinary differential equations. Take an interval curve. Then, again, you have this relation. So, your vector field at a point on the curve is the tangent vector to the curve. Now, these are two tangent vectors, so you can apply them to any function f. It means that x at gamma of t applied to f is f composed gamma differentiated, evaluated at t. So this is just, if you remember it from the first, second hour of the course, I don't remember. This is the way we differentiate along the curve. So we compose with the curve and we take the derivative in the parameter. Again, if we take f as a coordinate function, we are always in a local, in a coordinate patch, in a coordinate chart, and we have our local frame. So we take a coordinate function, then the jth component of our vector field is just the vector field evaluated at the coordinate function. So it is here you put the coordinate function, so it means that you take the jth coordinate of gamma. So we have gamma 1, gamma k, and these relations give us k ordinary differential equations of the form xj of gamma 1, gamma k equals gamma j prime, where xj is a smooth function from an open set of Rk to Rk. So what does it mean? It means that okay, this is not written down explicitly, but it means that an integral curve is just a system of ordinary differential equations with the starting point. So it's a Cauchy problem. You have all these k ordinary differential equations, and then you fix one point you want the curve to go through at a certain time, and you solve the Cauchy problem, and you get your integral curve. So it means that the flow, which is taking the integral curves for every starting point in some set, means to solve the Cauchy problem for any initial data in some set. So if you don't care, if you want to do it on the whole manifold, it means just solving the Cauchy problem everywhere. And I mean, it's finding a general solution of the system of ordinary differential equations, which has the starting point as parameters. Now, this is the theorem. It's a classical theorem in linear analysis that, given a vector field, you can locally solve it. What does it mean locally? Well, there are some conditions. I mean, can you read it? I hope. Well, that's too much, so don't care. Anyway, you have your function, you have your vector field. It's called f here, but and well, it has to satisfy some condition. If it's a smooth vector field, well, whatever. If it's a smooth vector field, it's fine. Lipschitz condition is satisfied. And you take any point inside your open set. You need that your vector field is bounded by the constant on the ball. Then you can find the flow. So you can solve it your ordinary differential equation. What's the point here? I mean, look at that. It's a common interval for all the solutions you find. So it means that, I mean, I don't know if you've studied that, but when you study ordinary differential equations, you can study them in two ways. Without entering too much into the detail, but the usual, the boring actually thing you do at calculus, cioè analisi 2, it's that you are taught countless names of dead people who solved some kind of differential equation, Riccati equations, Bernoulli equations, and blah, 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 blah. There are a lot, a number of them. Then at some point there were people studying them, but they also have a name of their own, like first order differential equations or constant coefficients differential equations, blah, blah, blah. And you have techniques for solving them. The other kind of thing you can do is studying them qualitatively. So you don't know how to solve the equation, but you try and say something about the solutions. If there is a blow up, so if at some point the solutions, on R, okay, one variable, you take a solution, it could happen that the solution blows up. It explodes. Try and solve anything like first derivative equals a power, and you will see phenomena like that, or a breakdown of the solution, so it just collapses, because the derivative goes to, for example, minus infinity or plus infinity, or other kinds of phenomena that prevent the solution from being defined all over the real line. So if you write down a differential equation, chances are that the solution, which exists because Cauchy, blah, 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 etc., are not defined globally on R. You need some estimate, Grunwald lemma or whatever, that give you estimates such that the solution is defined all over R. Problem is that many times the lifespan of your solution is depending on the initial conditions. So you don't have a common lifespan for all the solutions. Let's say you want to fix the value at 0 of your solution. So you say that u of 0 is something, and then you have your equation u prime equal blah blah blah. Now, what happens? It may happen that the maximal interval on which your solution is defined depends on the value at 0. So you cannot have a common time interval on which all solutions are defined with no regards of their initial data. So here is why we bother defining local flows, because maybe a global flow does not exist. Again, local flows do exist. If you have some, I mean, if your vector field is nice, okay. Now, the other phase of vector field flows, one parameter groups. Now we fixed the variable p inside our flow, and we obtain a curve. What happens when we fix the time? So if we look at where all the points go after some time, 1, at time 1, where do our points end at time 1? What we obtain is a function from v to m. Okay? So we denote it by phi with t, and it goes from v to m because it takes every point at v and it follows it along its own integral curve at time 1. Then we forget about the curve and we just take the point p and send it to time 1 for every point p. So we get a function from v to m is a smooth function, we can check it, and this happens, this weird relation happens. If you apply phi with t to phi with s of p, it's like applying phi with t plus s of p if everything is defined, obviously. If t, s, and t plus s are inside our time interval, and if phi with s of p is inside our set of definition. But if everything is defined, it works. So applying one function after the other is like applying a single function with the sum of the times. It makes sense, no? If we make everything go forward of 1 second, you would like to say, 1 time unit, and then we make everything go forward of another time unit. Is like, from the start, making everything go forward of 2 time units. Okay? A one-parameter group of diffeomorphisms is a collection of diffeomorphisms, f with t, from M to M with t in R, or not t in R, yes, such that this relation holds. I mean, now, if you look at this, here it's M, so we don't bother where the first map sends the point P, because they are all defined on all of M, and we live in R, so we don't need this condition. Okay? Second condition, at time 0, everything stays still. So the time 0 diffeomorphism is just the identity of our manifold. Third condition, the whole map is smooth, from R times M to M. It may look weird, but okay, take, I don't know, the sphere in R3. Take, let's write it down properly. This matrix. Which is a rotation matrix around the z-axis. And define your diffeomorphism as the rotation. Okay, there is some problem today. Hopla. As the rotation. So phi with t of a point P is just RT times P. Now, I hope it's, well, even if it's not obvious through the matrix form, it's a rotation of an angle T around the z-axis. So if you compose 2 rotations of angle T and S, you get a rotation of angle T plus S. These are all diffeomorphisms, these are rotations, and the sphere is invariant under rotations. And for t equals 0, you get the identity. And this is a smooth map because the map sending t to the rotation is smooth, and the map here is just a linear map. So it's a composition of a smooth map and a linear map. So this is, for example, a one-parameter group of automorphisms of the sphere, of diffeomorphisms of the sphere. It's in R3, but you can do it in Rn with respect to any n minus 2 axes. Okay. Even simpler example, here maybe, in another color. we take Rn, we take a vector in Rn, and we define phi with t of x to x plus tv. Again, this is a one-parameter group generated by the translations of V. So they're not really, I mean, there are geometric transformations that are somehow, well, the group words refer to these first hypotheses here. So the group is this first relation here. So that the composition between diffeomorphisms ends up as the sum of their parameters. Now, flows and one-parameter groups are linked. Given a one-parameter group of diffeomorphisms, we can consider the curve given by each point. I mean, you know the trick at this point. And the vector field given by the velocity of this curve for each point at 0 is called the infinitesimal generator of the one-parameter group. So, for example, for the translations in Rn, the infinitesimal generator of the one-parameter group is V, the vector we use for the translation, so that at each point of Rn, in the tangent of Rn, you get the V. And so it's a constant vector field. You can try and write down the one for the sphere, because I mean, it's the rotation around the z-axis. So, well, okay. If I got the signs right, so if I put the minus and plus on the anti-diagonal right, the infinitesimal generator should be the cross product between the z-axis, so E3, and the point. The point and it, well, it depends. I mean, there is a sign, but you can compute it because the integral curves of that. I mean, if you fix the point and let the time go, you get the parallels on the sphere. Because it rotations around the z-axis. If you take a point and follow it, it goes around the sphere and it comes back. So you get just. So for every one-parameter group of diffeomorphisms, you get a vector field, which is take the curve, take the velocity, and calculate it at the starting point. Well, a global flow is a flow defined on R times M. And every parameter group of diffeomorphisms is given by the global flow of its infinitesimal generator. So every time a vector field has a global flow, so for each initial condition, you can find the solution of the ODE system on the whole real line. So the lifespan of your solution is the whole R. So if every solution of your ODE system is eternal, that's the usual name, then your vector field is the infinitesimal generator of a one-parameter group of diffeomorphisms. So, talking about vector fields and talking about diffeomorphisms is somehow related. Moreover, if your vector field has a global flow, so if you can follow it for any time globally, your vector field is the same thing as a one-parameter group of diffeomorphisms. If you specialize it locally, every diffeomorphism is the time one flow of some vector field, but it is another thing, at least locally. Well, there are many, many links, so this is some links. So talking about transformations of your space, of your manifold, is like talking about vector fields. I've left one thing out. Why are they all diffeomorphisms? Well, this is, I mean, a thing you have to check and to prove, but it's true. So I mean, it's the same principle for which in R, you cannot have two solutions of the same differential equation that cross. So at one at one point you have just one solution of that differential equation, not many. It's the same kind of phenomenon. Now, Lie derivative. You have, we've learned to do, to take the differential of a smooth map. So we could, in principle, take the differential of the, for example, of a vector field, given that a vector field is a smooth map from M to the tangent bundle of M. And so we have the smooth map from M to the tangent bundle. We take the differential of these, and this will be a map from the tangent bundle of M to the tangent bundle of the tangent bundle of M. But things get more and more complicated while we go on, and this is not good. So in general, it's difficult to go on with this differentiation procedure. Also, we have the differential of a scalar function. If you take twice the differential of a scalar function, things get a bit weird, at least in this setting. Lie derivative is a way to differentiate things along a vector field. So you take a vector field. You take a local flow of x of your vector field near a point, and phi of t is the diffeomorphism obtained fixing t the time. So it's a diffeomorphism of what? Of a small ball around p. It's a local flow, and v is and the v in the definition of a local flow is a small ball around your point p. The Lie derivative of f along x is this thing. So, is the derivative in time at time 0 of the pullback of f through phi of t. So now, you are in a point. I won't draw the manifold. We are in the manifold, okay? We are at the point P. The same things works in Rn, and it presents more or less the same problems because this is all local, so it can be done in local coordinates. So we are at point P. And we are given some vector field. I won't draw the vector field. We calculated an integral curve for the vector field. So we have, locally at least, some integral curve. This is given by gamma of t equals capital phi of tp. And obviously, at each point you have your so here it's xp, here it will be another x, this is q, the xq, etc. And this is the velocity of your curve gamma. Now, what happens when we calculate the pullback via phi with t of f at a point P? So this is a function. So the pullback operator applied to f the result is calculated in P. I mean, the pullback operator on function is a weird way to define, to write the composition. So this is just F composed phi with T applied to P. Now T is P is fixed, sorry, P is the point. So this is just F of gamma of T. So the pullback takes the value of F at another point and brings it back at P. So we can confirm. Now, F is a scalar function, so we don't really need this, but we will need it for other geometric entities. But now the important thing is that this pullback is just F calculated at the point gamma of T, so further on along the curve. And now we take the derivative in time of this. So I think you can understand that given that this pullback is just F of gamma of T, taking the derivative in T and setting it to 0 is again the same thing. So it is X applied to F. Is the vector field X, which is in P, X of P is just the velocity of gamma, the tangent vector gamma. So by definition, this is X applied to F as a derivation. And this holds in every point, so it's just X applied to F globally. Now, probably if you never saw the Lie derivative, you don't see the point of this definition for now, but do you agree with the conclusion? So is it okay for everyone that the Lie derivative along X of F is just X applied to F, so is the X is derivation, so it's just this. If anyone has a question on here? Maybe, maybe not. No, okay. Hopefully not. So now we move on and do the same thing with a vector field. So Y is another vector field on M. Its Lie derivative along X is the same thing in principle. So this thing. Now, here there is a problem. We don't pull back vector fields. We push them forward. So this thing is not defined for vector. It doesn't make sense. Because if we have a vector field and any smooth map, we can push it forward, not pull it back. So the star should be downstairs, not upstairs. What can we do then? Well, the pullback via phi with T was a way to look at something which is at time T and pull it back at time 0. Okay? But this phi with T is a diffeomorphism and is a one-parameter group of diffeomorphisms. So instead of pulling back via the map, we can push forward via the inverse. So one way to take something at time T and bring it to time 0 could be to pull it back through the map or to push forward to the inverse map. So this is the important thing. For diffeomorphism, we define actually the pullback, even on vector field, as the push forward via the inverse. And now this is the fundamental fact. The inverse of phi with T is phi with minus T. Why? Because you remember, if you compose two of them, you sum the times, and the identity is at time 0. Okay? So the Lie derivative along X of Y is just the derivative in T calculated times 0 of the push forward of Y via phi with minus T. So again, now it makes more sense, because think about it. This will be important also Thursday. You are considering, you want to take a derivative, in some sense, you want to take the derivative of y along an integral curve of x. So you have an integral curve of x, and you have the integral curve, gamma, you have a point P, and for every point of your curve, also outside, but for every point on the curve, you have, this is not a tangent vector field, okay? Well, maybe at some point it's tangent. But it moves out. I mean, it's a vector field in the space, and we are looking at it it goes also on in the other direction. So y is defined also out of your curve, okay? It doesn't exist only on gamma, it exists everywhere. Now we are looking at it only on gamma. Gamma is a is an integral curve for x. And then we have the vector field y. Now, we want to make sense of the derivative of y along gamma. Okay? Why gamma? Because gamma is the integral curve that goes through P. For every point you have one integral curve. Now, what's the problem? With the function, you just take the values of the function and you take the difference of f of p, f of q minus f of p divided by t, and you let t go to 0. Easy. Now, suppose you have, so this is gamma of 0. And this is gamma of t. So you would like to write this thing. But it doesn't make any sense. Y of p, y with p lives in the tangent space. This is inside the tangent space at P of M. This is inside the tangent space at Q of M. So there are vectors which live in different vector spaces. We are not in Rk, in Rn. We are not in the submanifold case. So we could say, yeah, they're in different spaces, but we can take difference in Rn in some sense, maybe. It wouldn't make much sense, but we could at that point. Here, we cannot even do that because these are really two abstract vector spaces which are different. It's like taking the space of polynomials and the space of matrices and take the difference between a matrix and the polynomial. Okay. It doesn't make any sense. We need a way to bring one space to the other. Now, the push forward via phi with minus t at q, well, just writing like this is not really good. goes from, for example, tq, q is gamma of t, so if you push forward via phi with minus t, you go back of t in time, so you end up on p. So this is a way of taking the second vector space, tqm, and sending it to the first vector space, tpm. Bear in mind that all the phi's are diffeomorphisms, because therefore these are isomorphisms of vector space. So we are not like maybe sending everything to zero or on a subspace. It's an actual invertible operator between vector spaces. So now, once we pull it back, we can confront the value of y at p and the pullback of the value at q, or the push forward via the inverse of the value at q. Then we can take the difference, divide by t, and take the limit. So that's the whole idea. These local diffeomorphisms give us a way to confront what happens in different tangent spaces. Why? Well, because differentiating function is the first step, and it gives you differential one forms on one hand, and the way you differentiate them, so directional derivatives on the other hand. Now, think about a curve. I think you all know, at least you all have seen this once at least. If you take a curve in R3, for example, and you derive it, you have the tangent vector, the velocity vector. What happens if you differentiate the velocity vector? Maybe you normalize it and then you differentiate it. What happens? I hope you've seen it maybe in a physics course, or I don't know. If you differentiate it, you end up with something which is related to the acceleration. And in turn, the acceleration is linked to the curvature, to how much you are curving from a straight line. Okay? So if we want to talk about second order stuff, so the derivative of the derivative, so the acceleration, we need a way to confront vector fields which are on different tangent spaces. So a first instrument is the Lie derivative, which is not what we will be using because it doesn't work that well, but it's the first attempt. And the main reason I'm explaining it to you is because of the very construction of it. So the way it confronts probably two different tangent spaces. I hope it's clear. Now, doing the computations, I will be putting them in a notes file I will be uploading on BIP. I won't be doing them now. You can do local computations, or you can go in along a more theoretical direction. But anyway, the Lie derivative of a vector field y gives you another vector field, which calculated on a function f does this funny thing. So how do you read this formula? This part means that we apply y, which is a vector field, to a function f. We obtain another function, which is point by point, the derivative of f in the direction given by y, in a sense, and we apply x to this function. On the other hand, we do the opposite. We first apply x and then y, and this is the result of the Lie derivative of f. So it's a vector field that acts this way on f. I mean, you can show that this is a vector field. Namely, it's the commutator of the two vector fields. So given x and y vector fields, the commutator, or Lie bracket, it's related to the Lie derivative, is denoted by this symbol with square brackets, and is the vector field defined by this relation. So the one we saw before. If we write down x and y in coordinates, so x is xj dj and y is yj dj, then what does this mean? Okay, applying y to the function f means yj times the jth derivative, the jth partial derivative of f, sum on all of these, and this is a function, so this is a sum of yj partial derivative of f in the variable xj, sum over j. To this function we apply the field x, so we compute xh, the h partial derivative of the function we described before. And then we do the opposite. If you compute the partial derivative, remember yj and xj are functions. We obtain, we distribute the derivative with the Leibniz rule, and the second partial derivatives of f, so the h dj of f and the h dj of f here, cancel out, because if because the partial derivatives commute. So you end up only with the terms where you differentiate either yj or xj, and so you end up with this expression where the leftmost derivative is applied only to the coefficient of the vector field, because when you apply it to f, the terms with the same derivative, with the same second derivative of f, cancel out, because deriving first in the h variable or in the jth variable or the opposite is the same. So you end up with this expression. Now this expression can be written as a vector field acting on f, because this is the jth derivative of f, so you take this out to the right, and you end up with a vector field which has as the jth element this sum, which is a sum over h, which is a repeated index. So xh dh yj minus yh dh xj. So the coefficients of x times the corresponding derivative of one coefficient of y minus the coefficients of y times the corresponding derivative of the one coefficients of x. Which coefficient? Well, the one with the same index. Now, the Lie bracket has a lot of properties, among which the important one is the Jacobi identity, which is the following. So if you calculate all the cyclic permutations, so x, y, z, z, x, y, y, z, x, and you do the double bracket, you end up with 0. You may think it's, it may not seem important to you, but it actually is. The space of vector fields with the Lie bracket turns into what is called the Lie algebra. We won't be digging into that, but it's a thing, so you should be knowing it. Now, some properties of the Lie derivative. The Lie derivative is a derivation on the functions, because the Lie derivative is just applying a vector field to the function, so it's a derivation. It's a derivation also on the vector fields. Namely, if you apply it to scalar function times vector field, you end up taking the Lie derivative of f times y plus the Lie derivative of y times x, always along the same vector field. It's compatible with the Lie bracket, so if you take the Lie derivative of the Lie bracket, it distributes, and it's compatible with differential. Now, you actually don't know what this part is, so we will be seeing it now, very briefly. Differential one forms. Differential one forms are sections of the cotangent space, and sometimes the set of differential one forms is denoted by omega 1 of m. In RK, we can write differential one form like this, where the elements dx1, dxk are the dual basis of d1, dk. That means that if you apply, these are one forms, okay? These are differential one forms on RK, such that if you apply this one form to these vector fields, so the first one to the first one, you end up with 1. If you apply the first one form to any other vector field, you end up with 0. That's the meaning of dual basis. So given any local or global frame, you obtain a corresponding frame, coframe actually, on the cotangent bundle, which is this set of differential one forms, which are a basis of the cotangent space at each point of your open set. Now, given a vector field and the form, if you fix the local coframe and take the components with respect to it and with respect to the corresponding local coframe, you have that the action of the form on the vector field, because remember, a differential form point by point is a linear functional on vector fields, so it's something which takes a vector on tangent vectors. It's something which takes a vector and gives you a number. So that number is the coefficient, is the scalar product, you would say, between those two. Or if you imagine the one form as a row vector and the vector field as a column vector, is just the product, the dot product between the two. So is the product coefficient by coefficient between the form and the vector field. If we are taking the coefficients with respect to a frame and its corresponding dual coframe. Now the pullback of a differential form works exactly the same way. So we take local coordinates here and there, and we end up with the same formula. The pullback of alpha is this thing. You pull back just the basis of differential form. So you end up multiplying the row vector, so alpha is a row vector, composed with phi, obviously, times the Jacobian matrix of phi. So you have rho times the matrix. Or if you want to write, if you are looking at the cotangent space as a vector space, in that vector space with respect to the coframe basis, you are actually using the transpose of the Jacobian matrix. In contrast, as we saw before, for vector fields we are using the Jacobian matrix, and then the vector field is a column vector. So you could think about the subscript and superscript as identifying the coordinates of a row vector and of the column vector, respectively. Now, the leading derivative of the differential form is just wrapping it up. The definition is always the same: is the pullback of alpha via phi with t. You differentiate it at t equals 0. So it's always the same definition. Now, in coordinates, it's just that. You can do the computations and you end up with this. So it's alpha I times the jth derivative of xi plus xj times the jth derivative of alpha I. If you combine this with the basis for the cotangent space, or with a coframe, if you are working globally, you can write that the lead derivative of alpha along x is alpha j times the differential form given by the differential of xj, which is the jth component of x with respect to local frame. So the jth component of x gives you a function, and you take the differential of this function, which is the differential one form, and you multiply this by the coefficient of alpha, which is another function, plus the vector field x applied to the coefficient of alpha times the xi. Obviously here a summation on j is implied, and here a summation of I on I. So you have to sum these on j, you have to sum these on I, and then you get the result. If you apply this to a vector field, because the lead derivative of a differential form is again a differential form, you can apply it to a vector field, you end up, you just multiply this by a vector field, and you end up with this. This is the derivative along x of the function obtained by applying alpha to y, minus alpha applied to the Lie bracket between x and y. The first one is the lead derivative along x of alpha of y. So you get this nice formula, which is, it has much more. It has other meanings if we put additional structure, or at least we introduce other kind of geometric objects like differential K-forms. But for now, I mean, it's just it. And so I will stop here.